The afternoon session. The first speaker this afternoon, I'm very happy to introduce Misha Finkelberg from the Hebrew University, and he will speak to us about orthosymplectic bow varieties. Please.
So, thank you very much for the invitation. It's a big honor for me to talk here. Yesterday, Sasha Brewerman gave a list of Joseph's advices, some of which he was able to follow, some of which was not. My talk today will be a pathetic example of one particular small piece of Joseph's wisdom, which I was not able to understand. The mirabolic subgroup P in GLN appeared at least 50 years ago in the work of Gelfand and Kashdan, or maybe even earlier, but at least I learned it from the paper of Joseph's P invariant distributions on GLN and classification of unitary representations of GLN in non-Archimedean case. And one thing that I learned from it, that if you take the nilpotent cone of GLN, then it has finitely many orbits of this mirabolic subgroup, or in other words, if you take the product of the nilpotent cone and the vector representation itself, then the diagonal action of GLN has finitely many orbits. Well, everybody knows that the orbits in nilpotent cone itself are indexed by partitions of n. Then about 15 years ago, Roman Travkin discovered that if you consider orbits here, they're indexed by bipartitions of n. And I was very excited about it, and came and told this to Joseph. But Joseph explained to me that while the fact that the set of orbits is finite is important, the particular parameterization by partitions or bipartitions or whatever is nothing to be excited about. So I failed to understand this, and well. What is what? Sorry? Bipartitions, just couples of partitions that sum up to capital N. Two partitions of small sizes, the total size is capital N. Okay, so I will talk. Pardon me? Ordered, yes, ordered. Yes. Well, like, for example, 3, 1, and 2, 2, 1, something like this. Oh yes, certainly, yes. Shoji, for example, yeah. So I will talk about a work of Amichai Hanany, who in fact went to undergraduate school in here in Weizmann, as far as I understand. Pardon me? Pardon me?
There's no undergraduate school at Weizmann.
Sorry. Well, at least to my, I think I got my master degree from Weizmann, maybe. Okay, sorry. And Cherkis-Nakajima. And well, this is about Bow varieties. So the Bow varieties is a powerful tool to compute Coulomb branches and S-duality. So the general framework is that given an action of group G on a smooth fine symplectic variety, there is a way to associate to this a commutative ring object in the derived Satake category on the Grassmannian of G. And then you can consider the cohomology of the equivariant cohomology of the fine Grassmannian with coefficients in this commutative ring object, and the spectrum of this will be the so-called Coulomb branch of Gx, or else you can consider some enhanced version. So you take R and tensor it with so-called regular sheaf. Which under geometric Satake corresponds to the regular representation of the dual group. Okay, and then again you take the covariant cohomology of this, and this is equipped with the action of the dual group via this regular sheaf, and this is called the S dual of X, so it's equipped with the action of the dual group. But I will just use it as a black box, this thing. The Bow varieties will be used to compute many examples of these things. So I will start with a recollection about classical Bow varieties, Cherkis-Nakajima-Takayama, Bow varieties, not orthosymplectic. Okay, so they are built of two kinds of pieces. First is the so-called bifundamental or two-way blocks or pieces. And they are just the cotangent bundle of home from C V1 to C V2. So there's an action of GL V1 times GL V2 on this, and this is denoted as V1, V2 in this way, just a circle. And this is the first type of pieces. The second part of pieces is so-called triangle or NAM. And these are either cotangent bundle of GL V times this, in case V1 equals V2, And know that in this case, the stabilizer of a typical point is exactly the mirabolic subgroup, which I mentioned before. Or else, if V1 is bigger than V2, you take GL V1 times a certain Slodový slice. Well, Slodový slice to certain nilpotent element. Nilpotent element is V1 minus V2, and then many copies of just trivial block. And if V2 is bigger than V1, then symmetrically. Yes. So S is a Slodový slice. In GL V1 to the nilpotent orbit of this type. Namely, you take an element E here, and then this slice is E plus the centralizer of F for an SL2 triple containing this E. And it is this product, GL V1 times the slice, in fact, for arbitrary slice at all, as symplectic structure, invariant under GL V1, but also there is action of another group, because the centralizer of this nilpotent certainly contains GL V2. Okay. Yeah, just I fix arbitrary element, arbitrary triple, and then it gives rise to some particular slice, but this product will be always a symplectic variety with this action. And the key observation is that the S dual of the first type of block is the second type of block. So this is denoted by V1 cross V2. Yes. Yes, because for example, if V2 is V1 minus 1, then this will actually be all ones in reality, right? And the slice will be the whole of GL V. So in this case, V1 V2 is just the cotangent bundle of GL V1. Okay, and in case V1 equals V2, you have this version of definition. Okay.
So you have
pardon me?
the duality there and
Oh, S is for duality and for Slodový, yeah? Unfortunately, that's true. But, well, maybe let me denote Slodový by this. Yeah, that's also true. Relationship between V1, V2, and what else? So E is an element in this orbit, so-called hook type nilpotent. So its Young diagram looks like a hook. Okay. Last S is not Slodový, right? Thank you. Okay. So Now, how these are used? Well, there is a following notation, or maybe first let me define the Bow varieties. So a Bow variety is a Moore-Chikawa composition of these pieces. So in other words, you take you draw a diagram. It may be just a line segment or a circle, well, like V1, V0, V -1, V2, and then again maybe 3, and so on. So that they have some common vertices, and then two types of edges. And then you take the product of pieces along edges, and take Hamiltonian reduction with respect to sort of diagonal action of product of GL V's for vertices. And once again, it can be either a fine cyclic graph AN, or it may have boundaries. So it may end like this. Meaning that you have 0 here, nothing. Okay, and now the notation is that a Bow variety is balanced or co-balanced if for any triangle part, this the two vertices have the same dimension, or dually for any bifundamental part, the edge, the vertices have the same dimension. Okay, and now, pardon me? Pardon me? No group at all. Well, especially, well, no group at all. It was all killed in the process of Hamiltonian reduction. So now I said that these varieties are useful for the description of certain Coulomb branches, but also for Higgs branches, namely the usual quiver varieties. So any quiver variety is a Bow variety, and this is a theorem of Cherkis. For a type A, maybe a fine quiver variety. With frame. Like this. The corresponding quiver variety which is again a certain Hamiltonian reduction of something like bifundamental pieces, and also some fundamental for framing. So it's the Higgs, the Higgs branch EV is a Bow variety where, well, it is a co-balanced Bow variety. Wi is the length of chain Vi, Vi, and so on, Vi. And then you attach the next similar chain with Vi plus 1 to the right, Vi minus 1 to the left, and so on. Okay, and this is almost tautological and easy given this definition. But a hard theorem is due to Nakajima-Takayama. Is that, yes? Yes.
Is what we call a quiver variety automatically?
Yes. It may be singular. It has finitely many symplectic leaves. It's Poisson. It's a fine. When I write this, there's the categorical quotient. So you take the zero level of the moment map and then categorical quotient of this group. So it's an affine variety by definition, but maybe singular. That's what I mean.
So what is the theorem? I'm not sure. And you say in sense, just thought that.
What is a quiver variety, or what's the question?
So it would.
This is a Bow variety. This is a Bow variety. What is a quiver variety? So you take, again, the product over all edges Vi, Vi plus 1, and also times the product over all vertices T star home from CVI to CWI, the framing. Okay, and then this you reduce with respect to the product of GL VIs. They're very similar, only here you have bifundamental pieces and fundamental pieces. Here you have bifundamental pieces and triangle num pieces. Yes, absolutely. The classical Nakajima quiver variety, yes. Yes, so it says that the Coulomb branch of the same gauge theory is the balanced quiver variety, Bow variety, where just the same, you just replace okay, just the same, only you use so in particular the symplectic duality between the Higgs branch and the Coulomb branch amounts just to replacing two-way parts by triangle parts. Okay. Now, one other important thing about Bow varieties is the Hanany-Witten transition. Namely, it is some local law of again, swapping two-way parts and triangle parts, that produces not a symplectic dual, but isomorphic varieties. Namely, if you have V1 to V3, then the corresponding Bow variety is isomorphic to V1, V2 prime, V3, where V2 prime plus V2 is equal to V1 plus V3 plus 1. Yes? Yes. Thank you. And now, given an arbitrary Bow variety, using these Hanany-Witten transitions, isomorphisms, you can move all the, say, triangle parts to the left and all the two-way parts to the right. And then you will be able to say something more specific about this Bow variety. Namely, if we have purely triangle sequence like this, V1, V2, and so on up to Vn, this will be isomorphic again to some equivariant slice, like just for a single triangle part. So it'll be GLVn times a certain slice S mu, where mu will be Vn minus Vn minus 1, Vn minus 1 minus Vn minus 2, and so on. V1 under the condition that they all decrease. Okay. And somewhat dually, if we have only two-way parts, by the way, this is due to Nakajima. Then again, we have a similar isomorphism, namely this isomorphic to nilpotent orbit closure, where lambda again is the same thing, Vn minus 1, and so on, V1 under the same condition. And this is a very classical result. It's due to Kraft-Procesi some 50 years ago. Okay, and now, given an arbitrary Bow variety, we move all the triangle parts to the left, all the two-way parts to the right, and we just cook up a single thing from those two parts. So it follows that M O will be equal to the intersection of the slice with the orbit closure. And then again, due to this symplectic duality, it will follow that the dual thing will be equal to S lambda transposed intersected with O mu transposed closure. Okay, so this is a part of some general sort of triality due to Nakajima, Maffei, Mirkovich, Vybornov. But this is by far the most straightforward and clear proof of this triality using both varieties. Pardon me? Then it's not so, but well, if you're interested in particular in the computation of symplectical dual to this, you just find a sequence which realizes this way and use the symplectic duality of both varieties, and you are done. But the both varieties themselves form a much bigger class. It contains such intersections, but it contains many more things like slice and affine Grossmanians or Zastava spaces or many things of type A. Okay, so this was. Well, the pieces are just the same, right? Because yes, just by definition, it's tautologically the same. The cotangent bundle to home from CV1 to CV2 is just the same as cotangent bundle to home. But you have many other pieces, so so certainly given a long chain, you can just swap it as a whole, but you cannot swap it locally. Yes. It can happen that one of them is empty, then the other one is also empty. Like in the example that Inna's teacher of algebraic geometry likes to give. In fact, recently there appeared a paper which just classifies all the empty Boole varieties. I mean, it gives all sequences of V's which produce empty Boole varieties. Yeah, just many inequalities. Okay, so now let's go to orthosymplectic. Boole varieties. And then one first task will be to realize well the orthosymplectic quiver varieties this way. So quiver varieties in question are like this. Again, we have the usual quiver variety. But now all the spaces are equipped with forms, either symmetric or anti-symmetric. So I denote by plus if it's an orthogonal form, and then all the neighbors must be symplectic. So here it must be plus, here it must be minus, and so on. So the forms, quadratic forms, well, not quadratic, bilinear forms on the neighbors alternate. And then automatically, when you take the product of C VI tensor C VI plus 1, then it's already symplectic. You don't have to take the cotangent bundle because you tensor the forms opposite signs. So we define the quiver variety, or else the Higgs branch, again as the product of those pieces for edges, and then reduce it by the product of groups. The groups will be SP of VI's or SO of VI's, or there's a version you can take orthogonal groups disconnected instead of SO, special orthogonal.
Varieties, which works for alternative groups and then.
So you want to obtain something symplectic. So you need some symplectic structures. Certainly, you can use more general groups, but you need some symplectic representations.
Right, but is it just an ad hoc definition of general thing that gives you this for symplectic groups or orthogonal groups, and I'm sure that's previously for you.
No, just a particular definition. I don't know any more general thing. Okay, so again, if you are interested in the Higgs branch, then the same thing holds true. So similarly to what I had before, let's introduce the following things. Say U1 will be W1 minus V1, and then U2 will be W2 minus V2 plus V1, and so on. And then UN plus 1, the last one will be just Vn. And if, again, I have the similar inequalities like this, then the quiver variety will be isomorphic to the intersection of certain orbit closure and Slodoway slice. But now this partition is transposed of mu, and lambda is 1 to V1, 2 to W2, and so on. And also there is an interesting question, what is the ambient group? Before it was GLN, and now it's not quite clear. So the ambient G is determined by W1. So it can be either symplectic or orthogonal, just like this. Okay, so this is about the Higgs branch, and for Coulomb branch, yes. W1. So I set up the things so that they somehow decrease to the right. W1 is the biggest one, and it can be either symplectic or orthogonal. Okay, now for Coulomb branch, we will need the notion of bow varieties. And let me just note first that this Coulomb branch is only defined if there is no anomaly. Otherwise, it's nothing, empty. And no anomaly condition in this for this quiver gauge theory means that for a symplectic vertex, the sum of dimensions of its orthogonal neighbors is even. So, for example, you have a quiver variety like 2, and it's symplectic, and this is 1 orthogonal, then there is no Coulomb branch at all. Makes no sense. And the difference with the previous GLN case is that in GLN case it was cotangent type. Now it's not cotangent, because such a tensor product is not cotangent bundle equivariantly to anything. So now let me introduce Bow varieties, orthogonal or symplectic Bow varieties. Again, we'll have pieces. So this will be, again, the product, CV1 tensor C2. But now they must be of, again, opposite parity, like this. So this will be a symplectic vector space. This will be orthogonal vector space. And it's, again, by fundamental. And for triangle num pieces, then this is either SP V1 or maybe cotangent bundle of SP V1 times C V1 minus, and this is symplectic space, but not cotangent, as you see. If V1 is equal to V2, or again SP V1 times the Slodovitz slice of V1 minus V2, this. And note that for symplectic groups, just in order to have such an nilpotent element, you must have V2 of the same parity as V1, that is also even. It's okay. Or else you can have an orthogonal case, and this will be SO V1 times the slice to this. But here necessarily, again, in order to have an nilpotent element of this hook type, you must have V1 and V2 of opposite parity. So you cannot have V1 equal V2, for example. And this will cause all the following trouble. So we'll start now digging up the resulting mess. Okay. So these are the available pieces. And now for Coulomb branch, but maybe before I say about Coulomb branch, let me say what happens with S-duality. So S-dual of, say, 2m to n, say this is positive, this is negative, for example, is, I just take the dual group. The dual group here is SO2m again. and the dual group here becomes SO to n plus 1, right? And so again, they are of opposite parity. Fine. But now if I take the S dual of to m plus 1 to n, again, this is positive, this is negative, then this piece has anomaly. And so it is really a metaplectic dual. And metaplectic dual of this symplectic part. So here I will have to m, the usual dual, but the metaplectic dual of sp to n will be again sp to n. So both are negative now. Okay, so this is the rule how to how to swap the local pieces. And you see that exactly all the triangle parts appear as dual of the bifundamental two-way parts. Okay. And so now for the Coulomb branch of VW, if the framing appears only at symplectic vertices, then it is just like with GLM case. So once again, the Higgs branch will be equal to the orthosymplectic Bow variety, where Wi is the length of a chain like this, Vi, and the Coulomb branch again is the Bow variety, where Wi is the length of Vi, Vi plus 1, plus 1, I plus 1, and so on. And since, yeah, it's okay. So in fact, it may end up in Vi plus 1, as you see, because the parity of W is arbitrary, so it may be not very symmetric. Okay, but now we're in trouble if we have some framing at orthogonal vertices, because then we don't know what is the S dual. I mean, the framing at, say, the elementary one-dimensional framing at a symplectic vertex produces just a piece like this, just like this. And it is one of our building blocks. But there is nothing like this for orthogonal groups. So we don't know what to do. We need to know the S dual of a tangent bundle to SO K times C plus K tensor C2 minus, and we don't know what is this. But to this end, there is the following conjecture. Yes. Just a two-dimensional symplectic space. But if you have framing, then you will have something symplectic here, at least two-dimensional, or maybe bigger. And you would like to know what is the S-dual of this thing. Yeah, it may be bigger, but even for this, we already don't have anything like this, and we don't know what is the corresponding piece. But at least we conjecture what is the corresponding piece. And it depends on the parity. So you can either have SO 2k plus 1 times SO 2k plus 1 acting upon the cotangent bundle of SO 2k plus 1 times C 2k plus 1 tensor two-dimensional space. Okay, and the S-dual of this is supposedly SP 2k times SP 2k acting upon well, how to say this? So I have 2k minus, then I have 2k plus 2 plus, then 2k minus, but I do not take reduction at the border. So I just take this tensor product plus this tensor product, reduce it with respect to the SO2k plus 2 group, and that's it. I keep the action of SP2k on the border pieces. Okay, and this let me comment. So this cannot hold absolutely true only up to nilpotent, so to say, or DG enhancement. Namely, even if, say, k equals 1, k equals 0, the most degenerate case, then the left-hand side is just a point without any nilpotence, but the right-hand side is just by definition the product of 2 points, but over A1. So it does have something in negative homological degree. Okay, and also because the group is trivial, right? The group is, it acts on something non-trivial, but the group is trivial. And if you take the dual of, just by definition, you'll have Grassmannian, which is just 1 point, and you will take cohomology will be just one-dimensional space without no action of group. Okay, and if you formally compute the S-dual of the right-hand side, I mean, this is Murta-Chikawa composition of 2 things and of 2 elementary pieces, 2-way parts. For 2-way part, you do know how to compute S-dual, so you just compute the Murta-Chikawa composition of this, and you will obtain the cotangent bundle of SO 2k plus 2 with the action of SO 2k plus 1 squared. And it's not what we started with. I mean, there is a family which degenerates this cotangent bundle to that product, but they're not isomorphic as symplectic varieties with the action of SO2k plus 1 squared. So something is fishy here. It's only up to nilpotents. And the second part is the even case. So it's SO2k acting on the squared, acting on the cotangent bundle of SO2k times the standard representation tensor with minimal symplectic space. And if you take the S dual of this, what you get? You get SO2k, SP2k, SO2k again, and you only perform reduction with respect to the middle group, so you keep the action of the border group, but then it's possible to compute what you get, and what you get will actually have two irreducible components. It will be some intersection again of nilpotent orbit in SO2k, but it will be a very even nilpotent orbit, so we have two components, and the section with the slice will also have two components, and then you have to take just one of them, and that's the conjecture. But this one, well, any of the two irreducible components will be singular. So if you try to compute the S dual of it to go back, it makes no sense. We don't know how to define S dual of arbitrary singular variety. So something is not very good, but the good news is that even though this conjecture is somewhat unclear, the result is correct. So if you just define your bow variety in general with these pieces, then it works. So the main theorem of A.Hanany and Nakajima is that the Coulomb branch of arbitrary orthosymplectic bow variety is the corresponding bow variety where for framing W at an orthogonal vertex, W is the length of the piece SP to K, SO to K, SP to K, and so on. Pardon me? Okay. Okay, let me. So it starts with 2k plus, then 2k minus, 2k plus, and so on. So in case of SO 2k plus 1 vertex. Only starts with 2k minus, yeah, dual of SO 2k plus 1. And for SO 2k vertex, Wi is the length of the piece 2k plus, 2k minus, But then in the middle, you do have to draw something else. You need orthogonal groups as opposed to special orthogonal. And again, this will be just one irreducible component of a certain intersection of very even orbit closure and Sloterdijk slice. Okay, so if you follow this prescription, the resulting Bow variety will be isomorphic to the Coulomb range. Okay. Yeah. I denote this by the square brackets. Then again, you take the product of two bifundamental pieces, and you take Hamiltonian reduction with respect to symplectic group, but you keep the border. Okay, so this is the main theorem of A.Hanany and Nakajima, and also another important theorem is that the Hanany-Witten transitions also work in this context, just literally the same. So E1, E2, E3 is isomorphic to V1, sorry, 2 prime, V3, but only you have some parities. It's minus, plus, minus. Oh, sorry, minus, plus, again, plus, and then here minus, minus, plus, or some other variable. Okay, and then just a few examples. So the first one is if we take 2n minus and then attach nothing at all, it means you just take the Whittaker reduction, and what you obtain is the universal centralizer of the group SP to n and Lie algebra to n. Or else, if you take the same with orthogonal group, you obtain the universal centralizer of the corresponding orthogonal group. And it's Lie algebra. But if you want the universal centralizer of the even orthogonal group, and it's Lie algebra, then you would like to say something similar, but you cannot go from even orthogonal group to 0, because they are of the same parity, and that's prohibited. So you go to 1 and then to 0. Everything is positive. Okay. So now another example is the cotangent bundle to an orthogonal group. And this is very straightforward. So you take n minus 1, n minus 2, and so on. But you don't reduce with respect to SON, and you obtain this cotangent bundle, and that's just sort of tautology. But if you take cotangent, if you want to obtain cotangent bundle over sp to n, then you would like to draw the same thing, 2n minus 2n minus 1, But you cannot do this because 2n minus 1 is odd, and there is no such a symplectic group. So instead, you draw like this. But that's not quite the cotangent bundle. It's the so-called mock cotangent bundle. Again, you don't want to take the last reduction. You keep this. So because of this, there is an action of SP to n on this mock cotangent bundle, but only of one copy. On the usual cotangent bundle, there's a left and right action of the group. Here, only one copy acts. And there is also the moment map. It's a symplectic variety with Hamiltonian action. So there is a moment map to the symplectic Lie algebra. But now the funny thing about this mock cotangent bundle is the zero moment level. For the usual cotangent bundle, it will be just the zero section, the group itself. But now it's 2 to the power k copies, so to the power n, sorry, copies of SP to n. Okay, now, well, my time is through, so I will not give any other example, but I just will say one word that Coulomb branches like this, they realize certain slowly slice intersections with orbit closures, but not quite. So this will be certain covers of certain nilpotent orbits. And there are some stupid restrictions, like all the parts of mu in symplectic case should be even, in the orthogonal case should be odd. But more interesting restriction is that all these orbits are special in the sense of Lustig. No other orbits arise this way. And all the covers that arise, they are dominated by Lustig's cover. There is Lustig's quotient of fundamental group, and only such covers appear. On the other hand, almost all such covers do appear. Well, and if you take the corresponding Higgs branch, it will be related by Barbosh-Vaughan duality to orbits in the lengthless dual group. So that's all I can say. Thank you very much.